Hello everyone, welcome to our presentation on neural network-based digital twin for impurity gas monitoring. Our team members are Bojo, Shu, and Omar. For this project, we developed a neural network to predict the ultrasonic response through the pre-helium. First, I want to introduce our experiment setup, which includes an ultrasonic test system and a gas backfill system. The data was generated in a pure helium environment and using the generator to produce excitations with different frequencies, amplitudes, and burst cycles. 2,351 pairs of excitation and response waves are collected. Then the impurity gas was introduced into the chamber for further testing.
We first set out to design a neural network based on the DeepONet architecture, where a function would be fed into a branch network and a time value would be fed into a trunk network. Despite various attempts, we were not able to obtain correct predictions. Our main hypothesis is that this was due to the large number of inflection points in the data we were using. We then moved to our final architecture, which is a multi-layer perceptron neural network. The MLP operates as an image-to-image function. The input is the induced wave sampled at 251 equally spaced points from 0 to 40 microseconds. The training data is the wave captured by the second transducer, truncated from 145 to 215 microseconds and sampled at 351 equally spaced points. The sampling points are held constant for all entries. The MLP itself consists of a 251-node input layer and a 351-node output layer. The depth and width will be discussed in detail in the tuning section. A sign activation function is used and is not applied to the output layer.
70% of the data was used for training process, and we used the Adam W optimizer for better training results. We trained for 2000 epochs with a batch size of 256 and stored the training loss history after each iteration. 15% of the data was used for validation. On the bottom is the graph of results for the grid research. On the bottom is the graph of the results for the grid search. After the grid search, we determined the optimum hyperparameters of our model. The optimum width and depth were chosen to be 350 and 7. Based on this structure, we tuned the learning rates and the weight decay. The best learning rate is 1 to the minus 4, and the best regularization is 1 to the minus 7. Then we used the rest 15% of the data for testing. In the middle is the graph for the loss curves. The losses decrease rapidly before 250 epochs and converge around 2000, with no sign of overfitting and underfitting. On the right are graphs showing the ground truth of some testing data and the model predictions.
After the digital twin is trained and tested, we further conducted some application tests. What we did is we introduced some impurity gas, that is the air, gradually into the chamber. And at each impurity gas level, we collected the experimental waveform, that is the red waveform. And what we compared is the prediction from the digital twin, which is shown by this blue waveform. So we compare the TOF of them, and we can determine the percentage of the impurity gas. That is the value outside of this parenthesis. And inside of the parenthesis, that is the true air percentage from the mass flow controller from the experiment. So we can see that in these diagrams, at different impurity gas level, the predicted concentration is very close to the true concentration here. And we did this test under 5 different kinds of excitation, 5 arbitrary sinusoid bursts. So we can see here in each case, the predicted concentration is all close to the true concentration. The values is around this diagonal direction. And eventually we did some noise quantification test. So we add some Gaussian noise to the input. So when the excitation are getting more noisy, the output is also getting more noisy. So we'll have some uncertainty when we determine the air percentage. So we ran in the forward direction of the neural network. And we can see from these diagrams that as the noise level increases from 10% to 50%, the uncertainty region, that is the 3 sigma region, is enlarged. although it's enlarged, but it's still overlapped in this diagonal direction, which means although there are some uncertainties, the predicted concentration is still very close to the true concentration here. It means that our model, our digital twin, is quite robust to the noise. These are all the results we got from this project. And the conclusion here is we train the digital twin based on the pure healing environment. And this digital twin can always be referred back when we have some real monitor data. So we can determine the impurity gas concentration. So the next step would be to consider two impurity gases and also the temperature variation. That's all for our project. Thank you so much.